I'm sorry? I know I have a new stand now. Extravagant, but this one actually has the little screw to hold things in. Okay, so we've now finished chapter 3, except during today's lecture we will go back and do one theme from section 6, which I'm going to skip for now, and you'll hopefully see now why this is an important theme to do. So our goal in this chapter is to try to understand functions by knowing things about their zeros. Okay? And so the question is, if I know things about zeros, how much does that tell me about the original function? Do I completely understand the function, or do I need more information? So let's take a simple example. I'm thinking of a quadratic polynomial, and you can ask me two questions about its zeros.
Where are they?
Where are they? Right? They're at 1 and minus 1. I'm not that original, it's early. What quadratic am I thinking of?
X squared minus 1 equals 0.
Nope. I'm thinking of 24601 to the 1701 times x squared minus 1. And so if you really know me, you can figure out why I've chosen those two numbers. Okay. Now that I'm at Williams, I should probably update at least one of the numbers, but old habits die hard. I'm sorry? Nope. No one knows 24601? If I sang it, it might be better.
It's Les Mis.
Yes, Les Miserables. Very good. Cultural reference of the day. Jean Valjean. Okay? Yes? So, why was you the one who guessed, Joe? Why were you so off? You weren't even close. I mean, look at how much you were off by. I mean, you're not even close to what I was thinking of.
They have the same zero as in function.
Oh, they do have the same zeros. So here, we'll call this, for me, maybe we should do P for professor. And we'll do J of x, which was the more mundane x squared minus 1. Now, let's look at the ratio. Which way do you want to do it?
Let's do J over S.
Well, I was going to say, since my Sox have definitely made it to the next round and your Tigers are still status indeterminate, I think we'll do it this way. Could use a y, and definitely then y would belong on the bottom. But if we do it this way, we get 24601 to the 1701. So this should be a very obvious function to notice a property about. Constant. So what happens here is if I understand the roots perfectly, I differ by a constant. Okay? Is that the only possible difference I could have? So if I give you two functions and they have the same zeros, do they have to differ by a constant, or could there be something else? Well, so here I'm saying I'm thinking of a quadratic.
Yeah, you told us it was degree 2.
So since I told you it was degree 2, yes. So can you give me an example? So we have j of x was x squared minus 1. Can you give me another function? Yes.
To the 4th.
When I do x to the 4th, it's going to have different zeros.
I mean, minus.
I'm sorry?
Like minus 1.
X to the 4th minus 1?
Are you looking for a function that has the same zero?
I want a function that has the same zeros as this.
With the same multiplicity.
With the same multiplicity.
Oh.
So, if you have a zero of multiplicity 5, it's not the same as having a zero of multiplicity 1. So can you give me a function that has the same zeros as this, but differs by more than just a multiplicative constant? Or is it impossible? Does real analysis maybe have one good thing going for it? So can you give me a function that's never 0? E to the x, right? We're in the real case now, right? So actually I was thinking of e to the 1701 x minus 24601. X squared minus 1. And now, if I look at g of x over j of x, I get e to the 1701x minus 24601. This function is not constant, but it does have a nice property. What's the nice property this has? Never zero. And in fact, it's never zero even if we regard it as a function in the complex plane. So the idea is, if you know zeros of a function, you do know a lot about the function. But you could be off by a multiplicative factor. And that multiplicative factor could have x dependence or z dependence. The question is, how badly can it depend? And the result we're going to get is, if two functions have the same zeros, they differ by the exponential of a function. And an exponential of a function will never vanish. Okay? And so now I'm going to go back and prove a theorem from chapter 3, even though we've only been in chapter 5 that long and we're really not going back that far. The idea is now, this is why we want a theorem like this. So, assume f is holomorphic in a simply connected open set omega. Then there exists a holomorphic G such that if f is never zero, then f of z is e to the g of z. Okay? So the only holomorphic functions that are never zero can be put in the form of e to the g of z. You give me a holomorphic function that's never zero. I'm sorry?
4.
Thank you. I was hoping you would say that rather than saying e to the z. Right? Can we write 4 in this form? Yes, equals 4 to the e to the log of 4. Works. Okay? So obviously this is not the proof. So if it's a constant function, this is not that impressive. Right? The impressive part of this theorem is that even if the function is allowed to vary, it's still true. Clearly, anything of the form e to the g is never going to have zeros. So I could even go if and only if. If f equals e to the g, then f is never zero. That direction is really not that interesting. Okay? The interesting direction is, if you are never zero, you can be written like this. So in some sense, there's a logarithm that I can define. Yes?
Is the implication of the theorem that g of z is like a log of
Yes,
f of z?
yes. That g of z is essentially the log of f. Okay. Time to prove it. So you've all, of course, read chapter 3, so you've all read the proof, so you all know how it does. But if you don't have it on immediate recall, which words in the statement of the theorem should give you some idea of what we want to use? Simply connected. So as soon as we see simply connected, what do we have? What theorems are at our disposal? So if you have a region that's simply connected, there's a very nice result we have.
Holomorphic functions have primitives?
Holomorphic functions have primitives. And in fact, we can define a primitive by integrating over a path. Right? So, as simply connected, primitives exist. And can be defined by integrating over a path. So the hardest part now is to figure out, well, what path do we want to integrate over? There are so many different possibilities. Okay. So proof. So let's take some point z0. Because the way it always works is I need some point to start my path. And now, given any point z, I take a path from z0 to z. And I'll call that game of z. If I, in honor, we did the photon last time, if I could draw a Higgs boson field in honor of the Nobel Prize, I would try to draw that. But let's take this as my path. How many of you like that choice of path? Does it matter what path I take? Why not? It's simply connected. So, as simply connected, answer is independent of path. So I just take some path in my region from z0 to z. The book calls this path gamma. I like to call it gamma of z to remind myself. So I'm going to define g of z. So clearly I have to integrate something over the path gamma of z. Right? I can't use z as my variable of integration because that's the endpoint of the path. So the hardest part in this proof is figuring out what do I want to integrate. So 1 over f is a possibility, so we'll have a list. We can all vote. All votes aren't equal, but we can vote. F prime over f. That one. Any other votes? E to the f. That's fine. It's contingent. It's the third party. Okay. Literally. And then there's one other natural candidate. If you're going to make a list, f should be on the list, right? So we have several candidates. What do we want g to be? We're thinking g is the log of f. So if g is the log of f, what should g prime equal?
F prime over f.
It should equal f prime over f. Well, if g of z is equal to some integral, then g prime, whatever the integrand is, okay? So again, I can race through material and just write down things. I'm happy to do that, and we can cover even more material in the course. There's at least 2 semesters worth of material that should be covered in complex analysis before you go to grad school, at a bare minimum, okay? If you want to, I'm happy to try to sprint through the book, but I don't think that's going to be what's most useful for you later in life. I want to really try to emphasize how you get to these stages, how you figure out this is what we should do. Who would have thought to integrate f prime over f? Well, you don't have that many possibilities. Try a couple of things, see which ones work. But if I'm thinking g is the log of f, then g prime should be f prime over f. So this tells me this is a really good thing to integrate. Should I put a 1 over 2 pi I here? I'm sorry? So should I put a 1 over 2 pi I? You might.
Okay.
There's more of you than me. I mean, I'm always amazed that students never rush their professors. Pencils, caps off.
Ready.
For the record, that was Pat who said he was ready. So if anything ever happens to me, now you know why this is being recorded. What a YouTube video, calculus professor slaughtered by students. So why should I put in a 1 over 2 pi I? Why should I not put in a 1 over 2 pi I?
It's a closed contour, then 1 over 2 pi I kind of makes sense.
Okay, if I do a closed contour, I want a 1 over 2 pi I. Whenever I have closed contours, I want 1 over 2 pi. Well, this is just half of a closed contour. What would happen if I put in a 1 over 2 pi I? What would g prime equal?
1 over 2 pi.
So g prime would no longer be f prime over f. So this is why I'm not putting a 1 over 2 pi I here. Okay? So again, I really want you to get a sense of why we're doing what we're doing. All right, now we know g is a primitive for f prime over f. So it's now a question of, can you unravel a definition? If g is the primitive for f prime over f, what's the derivative of g? Right, by definition, right? By definition, g prime is f prime over f. I remember being stuck on a homework problem my first year at Yale, and it took hours before we finally realized the proof was by definition. By definition, G prime is F prime over F. Now it turns out that I'm going to want to change this a little bit. What's the easiest place to evaluate this function? Not 1. So 1 is a special number, but does 1 have any occurrence in this problem? No. So 1 is wrong. It's a good thing to try, but Z is my well, I am evaluating the integral at Z. So what value of Z should I take? E. Not E. Not 0. I'm sorry? Z naught. Why Z naught? It's the only point I know! Right? If you look, the only thing I know is there's some point Z naught. Okay? So let's evaluate this at Z naught. If I evaluate this at Z naught, I get G of Z naught is 0. G of Z naught equals 0. What do I want to happen when I put in Z naught? What should it be?
F.
So I would have F of Z naught is e to the G of Z naught. If I took logarithms, I would basically want G of Z naught to be like the log of F of Z naught. Right? This is basically forcing me to choose a function G such that G of Z naught is forced to be 0. I don't necessarily want that. So I should fix this. What can I do to this function without destroying the primitivity of G of relative to F prime over F? Add a constant. So we can add C naught. And hopefully now you get a sense of why we're adding C naught. Because I want to make sure things are going to match at Z naught. So choose C naught so that, let me make sure, it's the correct way. Okay. Such that e to the C naught is F of Z naught. And so really now what we're getting is G of Z naught is C naught, and I'm choosing it this way. So I'm essentially choosing it to be the logarithm of F. And so again, hopefully this is now a natural thing to do. Okay. Any questions so far on why this is a primitive, why we put in the C naught? It's independent of the path. The derivative is the right thing. So we're almost done. All we have to do now is show that what we end up with is F is equal to e to the G. So let's consider F of Z e to the negative G of Z. What should that equal? That should equal 1. How can I show this function equals 1? So I believe F is e to the G, so I'm multiplying by e to the minus G, so this should be 1. So I'm asking you, how do you show a function as 1?
Take derivative at 0.
So if we take the derivative at 0, that almost is enough.
And then show it's 1 at 1 point.
And show it's 1 at 1 point. Okay, do you have any idea of what point we should use? Z naught, right? There's no other point to check. That's the only point we know. So at Z equals Z naught, get F of Z naught e to the negative G of Z naught. But G of Z naught is C naught, so we get e to the negative C naught. E to the negative C naught is F of Z naught inverse. So we get F of Z naught 1 over F of Z naught equals 1. Am I allowed to have 1 over F of Z naught? Why? Yes, my function is not 0, so I can divide by this. So everything is well behaved. Okay. 1 point down, infinitely many to go. Right? We've just shown that at least at the point Z naught, this function is 1. Now we need to show it's 1 everywhere else. And if this is 1 everywhere else, then you just multiply both sides by e to the G of Z. So Pat suggested that we take the derivative of this. Why should we be thinking of taking derivatives of this? So again, I like the fact you take derivatives because we can. So one thing is, if the derivative is 0, then we know it's a constant. But what in this problem makes you happy about taking derivatives?
We know the derivative of g in terms of f.
Good. We know the derivative of g in terms of f. And when you take the derivative of an exponential, you get back the exponential plus the derivative of the part over there by chain rule. So again, this is a great thing to try. This is a very powerful technique, writing it like this. If any of you have seen like proof of irrationality or transcendence of certain numbers, you have polynomials like this all the time. This is often used in the proof of transcendence of e, statements like this. So now apply d by dz to f of z e to the negative g of z. And we'll just get, product rule. It's been so long since we've done one of these. F prime of z e to the negative g of z minus f of z g prime of z e to the negative g of z. Okay? I can factor out a e to the negative g of z, and I'm left with f prime of z minus f of z, and g prime is just f prime of z over f of z. Do I have to worry about the f of z in the denominator? No, it's never 0. So it's equal to e to the negative g of z times 0, so it's 0. So f is never 0, so we're okay. And that's the proof. We now know that this is a constant. The constant equals 1. Therefore, f of z e to the negative g of z is identically 1, which implies f of z is e to the g of z. True. Okay? So this is an amazing fact. If I give you a holomorphic function on a simply connected set, and it's never 0, I can write it as the exponential of something. So the goal in what we're going to be doing in Chapter 5, and Chapter 5 is a rich, beautiful chapter. There's more in it than we can cover. So for now, I'm going to hold off on doing Jensen's formula. I'm going to hold off on doing Hadamard products. We may come back to that. I hope some of you will choose topics to present to look at in further detail to talk to the class towards the end of the semester. If not, I get to choose the topics. So this is your chance to control a little bit of where things go. I want to get into Weierstrass products in terms of writing a function in terms of its zeros. And for a lot of things, it's very useful to write things in terms of their zeros. So if you go back to polynomials, where we write the polynomial in terms of the roots, you have that little extra constant factor outside. And in general, you could have something worse. You could have an exponential. But if I tell you I have a polynomial of degree 2, then when we're playing the game, what polynomial is Professor Miller thinking of? You can only miss by a constant. If I, however, weaken things and say I'm not even going to tell you what degree I'm thinking of, I'll just tell you the zeros and the multiplicities. You can get that, but you may miss by an exponential factor. So the natural question we want to ask is, if I give you a sequence of zeros, does that uniquely specify a function? So, does a sequence of zeros uniquely specify a function? And if you want, we can make an assumption about how many zeros we're talking about. How many do you want to talk about? I'm sorry? Finitely many. That's a good case to look at. What else? Finitely many. What else could we consider? Okay, be more specific about infinitely many. Countably infinite. Countably infinite. Having a function with uncountably many zeros scares me a little bit. In a case like that, you would almost surely have what? If you have uncountably many zeros. Probably. So when you have a sequence of uncountably many zeros, something's going to happen. So when we're looking at sequences of zeros, there's a phrase we had, this accumulation point. So if you have uncountably many, this is what you should do. Take the plane and just divide it into squares of length 1. Alright, as much fun as it is to draw the squares, I will stop. Alright, so keep going like this. You have countably many squares and uncountably many zeros. What do you know?
There must be
There must be
uncountably many in some square.
There must be uncountably many in some square, which means there's infinitely many in one square, which means there's an accumulation point in that square. Okay, technically maybe the accumulation point's on the boundary, doesn't matter. There has to be an accumulation point. And now that we have an accumulation point, it would be identically 0. So it turns out, if I give you uncountably many zeros, is there a function that has zeros only at those points? Unless those points are everything, the answer is no. The function is 0 everywhere. Okay, so uncountably many is not that bad. What if I only give you finitely many zeros? Can you give me a function that only has finitely many zeros? And let's say the points, so let's do the finite points. A1, A2, AN. Can you give me a function that vanishes at those points and no other points? X?
Z minus A1, Z minus A2.
So f of z, z minus a1, dot to dot. It could have.
Yeah.
Absolutely. Any other functions work?
Yeah, constant.
I could multiply by a constant. What else? Exponential. Could I multiply by anything other than a constant or an exponential? Why not?
Because it changes zeros, and if it doesn't have zeros, you can write it as an exponential.
Ah. So the thought is that if I try to do anything else, I would introduce a 0 somewhere. So imagine h of z has the same zeros and the same multiplicities. So now we study h of z divided by f of z. Is this function holomorphic? Or are there places where the function blows up?
I guess we don't know. You don't know, like, the behavior of H of Z and F of Z around those zeros, right? So,
Well, okay, so does everyone agree that if we stay away from the zeros, this is okay?
Yeah.
So the only issue is if we're at a 0.
But they're all removable.
They're all removable singularities,
So,
right? They've been married, they've been matched together, right? The zeros from one have been matched with the zeros from another with the same multiplicities. So if this vanishes to order 5, this vanishes to order 5 at that point. If I have removable singularities, I can remove them, hence the name, right? So I remove all singularities, removable singularities. So now I have a holomorphic function, never 0. And so I have h of z over f of z has to equal what? Has to be e to the g of z. Because h over f has no zeros. As h over f is 0 free and holomorphic. Therefore, I get h of z is e to the g of z f of z. So h differs from f by an exponential factor. We've now handled the case of finitely many. Quick question? So we have completely classified functions. If I tell you the zeros, if there's uncountably many zeros, I'm thinking of the 0 function. If there's finitely many zeros, I'm thinking of this polynomial up to an exponential factor. Would it be enough to give you 1 or 2 points to where I evaluate this function to figure out what that exponential factor is? Question?
I had a question on for the uncountable case.
Yes.
Why isn't like just the real part of z?
Is that holomorphic?
Does it have to be holomorphic?
Yes.
Oh, all right.
So yes, so if I'm not considering a holomorphic function, all bets are off. And so it becomes a very interesting question. If I go back to real analysis, if I specify the zeros of the function, does it uniquely determine the function? And we actually had a really great bad function from real analysis. X cubed sine of 1 over x. So the plot of this was something like that, where I have infinitely many zeros in a small neighborhood of the origin, but the function is not 0. So an accumulation point for a real variable function, even if it's differentiable, is not enough to imply the function is identically 0. So complex analysis is very different. If you do analytic number theory and study things like the Riemann zeta function, these become extremely useful results to have to allow us to classify functions. Part of chapter 5, which I'm not doing right now, is talking about the order of growth of a function. If a function grows at a certain rate at infinity, that will actually tell you something about how many zeros it can have. And there's sometimes ways to estimate the growth of a function. So again, there are too many topics in complex analysis to do in just one semester. I have to pick and choose. What I'm trying to do is give you a bunch of scattered topics so that if something comes up that you actually need for your research, you have a starting point to then build upon. So, good question. You're very different from real. Any other questions on uncountable or finitely many? Alright, so what are we left with then? We're left with what happens if you have countably many zeros? Does that uniquely determine the function up to a exponential factor? Well, what would be your first thing to try if you had to guess what the function should look like? So if I give you countably many zeros, we'll call them an, and goes from 1 to infinity. So what function am I thinking of? What would you guess? It's okay if the guess is wrong. I haven't even told you what the ANs are. That's what the book was thinking of. That's what my former suite mate was thinking of. What am I thinking of? What would you guess? What's the simplest thing to guess? I don't care if it's right.
24601, the 1701 sign.
What is the sign fixation? Come on.
Cosine.
There we go. No. I'm not telling you what the ANs are.
Just an infinite sum.
An infinite sum?
Like z minus.
All that.
Sum or
Z minus A
not
one,
infinite
Z
product,
minus
right? Try f of z is the product n goes from 1 to infinity of z minus an. So hopefully this is supposed to be a natural thing to try. It generalizes what we have in the finite case, right? So you are welcome to go to the probability videotape from today. I gave my students the sum of n times 1/2 to the n. And I asked them, what's the very first question you should ask about this? Right, that's what they said. I said, the first question you should ask is, who cares? And then I actually explained why you care about this. But then the second question you should ask is, does it converge? What is the limit? So now, what's the first question we should be asking here?
Why do we care?
Oh, very good. All right, email me. That's definitely worth an email. Yes. So the question is, why do we care? Well, the reason we care is we're trying to solve this problem, which is written immediately above it. Right? So now that this is hopefully motivated, now what question should we ask?
Does it converge?
Yes. Does it converge? And if the answer to that is yes,
Does it converge?
what does it converge to? So the question is, can you give me an infinite sequence of ANs such that this converges? So here's the challenge. Give me an infinite sequence of ANs so that above converges. For some z not equal to what? Can you give me a value of z where this product converges?
A1.
A1, another value.
A2.
Right. So I want z to be outside this set. Based on the characters I have in this class, I think I have to be very, very careful. Yes, it will converge at A1. Yes, it will converge at A2. Wow, I'm so thrilled, right? This is not an achievement. It's like a Taylor series that converges at 0. Because you write it out at 0. It's f of 0 plus 0. Right? That's not an achievement. I want it to converge for one value other than the a's. So can anybody give me a sequence of ANs where this will work? Yes.
1 over 2 to the n?
Okay. Try AN equals 1 over 2 to the n. We get a product that equals from 1 to infinity of z minus 1 over 2 to the n. Okay. We are taking a digression from the book. I'm not jumping immediately to Weierstrass products. I'm trying to motivate why Weierstrass products are done the way they are done. Weierstrass is a very interesting mathematician to look up in terms of his career path. It is not the standard one to get to mathematical excellence. Right? Does this function converge?
Depends where.
Okay, so can you give me a value where it converges?
0.
It converges at 0. Okay? So we win, okay? 0 is not on the list, but I will... anybody watch How I Met Your Mother? No fans? So did you watch this week's episode? Oh, okay. In this week's episode, there was a dispute between two people, and they had to have somebody arbitrate their dispute as to whether or not this was an acceptable solution. And so I agree that it converges, but I have issues with what it converges to. And so we have the product n goes from 1 to infinity of z minus 1 over 2 to the n. At z equals 0, we get what? 0. So I would say this is an unacceptable solution, because the goal is I only want to vanish at the a's. This introduces an extra vanishing. Introduced extra vanishing. And then just for the record, Craig is not a plant in this class. He's doing this on his own volition. Let's see how much of an issue I have with Craig's solution. Can anybody give me another point where this converges? 1. It will converge at 1.
1.
At z equals 1.
That's one of the AI stuff.
I'm sorry?
That's one of the AIs.
It's one of the other. Alright, so let's take something else. Let's take root 2 over 2. What do I get if I plug in root 2 over 2? So I have root 2 over 2 minus 1, root 2 over 2. Actually, technically, if I put it in equals 1, I'm actually okay. But that's fine. So if I take root 2 over 2, do you agree that eventually every factor is less than 3/4? And I keep multiplying something at most by 3/4, by 3/4, by 3/4, by 3/4. What do I get? If the absolute value of z is strictly less than 1, what do you think we get? 0. Nice exercise to show that you get 0. So not only are we getting additional zeros? We're getting the function to be identically 0 inside the disk. What if z is greater than 1 in absolute value? What do we get? That diverges. Okay. So, I'm sorry? So now 1 becomes interesting. The only hope we have is to take some z of absolute value 1. Okay? So, if z equals 1, let's see what we get. We get 1/2. Then 1 minus 1/4 is 3/4. Next one, 7/8. Next one, there's a chance, right? We have a chance of convergence, right? This could converge. What do you think? I mean, the factors are getting close to 1 pretty fast. What should we do? You should immediately be having a Pavlovian response now. Take logs, right? Whenever you see a product, you should immediately think, take logs. Right? It should be instinctive. If you want, I will get a little bell. I don't mind putting something like this on my expense accounts. Ring the bell, okay? We'll play even one of the disco songs. Right? The log of the product n goes from 1 to infinity of 1 minus 1 over 2 to the n. Well, if I'm trying to look, really the first couple of terms don't really matter. This is the same as the sum, and it goes from 1 to infinity of the log of 1 minus 1 over 2 to the n. And I want to understand, what does that look like? The only thing I'm afraid of is that this product could converge to 0. If it doesn't converge to 0, I'm fine. I'll at least have 1 point. Yes?
How do we switch between product and sum?
The log of a product is the sum of the logs.
Right.
This is why we have this Pavlovian response. Whenever we see a product, we want to take the logarithms because we understand sums better than we understand products. Alright, so how should I understand the sum of the logs of 1 minus 1 over 2 to the n? I can break it into two parts. The sum n goes to 1 to big N minus 1 of the log of 1 minus 1 over 2 to the n. And that's going to be just some number plus a sum n goes from big N to infinity of the log of 1 minus 1 over 2 to the n. So the only danger I have is if this product is 0, I'm upset. If this product is 0, what is its log going to be? I'm sorry? Diverges to negative infinity. So as long as this sum is not negative infinity, the product won't be 0. So all I have to do is show that this is not going to minus infinity. Okay, all I have to do is show that this converges. Does this part here matter? No. So all it is this negative infinity. Well, we use the log of 1 minus u is u minus u squared over 2 plus u cubed over 3 minus dot, 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 dot. So, and if I stop after the u squared over 2, I'm underestimating, right? I want to show that this is not negative infinity. Oh, wait, no, sorry. This is the log of 1 minus u, not 1 plus u. All the signs are negative. Sorry, all the signs are negative. Okay? So, what can I do? I want to show that this thing is not negative infinity. If I drop this term, I make things worse. So this is one of the big themes in the chapter in terms of analyzing this. They often say, let's assume z is at most 1/2 an absolute value. So over here, I can assume u is small. If u is small, the log of 1 minus u is greater than or equal to u over 2. And so, if u is sufficiently small, u squared is going to be much smaller than u. U cubed is going to be much smaller than u squared. I can drop all the denominators and estimate this with a geometric series. And so the sum of all the stuff at the end would be at most u squared over 1 minus u. And if u is really small, well, it would be at most u over 1 minus u. And so if u is really small, it's not going to be able to contribute more than half. Okay? So carefully, negative u squared over 2 plus u cubed over 3 plus dot 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 dot. I'll drop the negative sign here. Now I want to see how large could I make all of this. The largest I could make this is less than equal to u squared plus u cubed plus dot dot dot, which would be u squared over 1 minus u. And if u is less than a half, I can make this really small. And so you just have to figure out exactly how small should u be. Well, my u is going to be 1 over 2 to the n, so eventually this is going to be so small that the stuff over here can't be more than half of u. So this whole subtraction is going to be at least u halves. Okay? Now that we have that, what do we have? So we would get the sum, and it goes from n to infinity, of the log of 1 minus 1 over 2 to the n would be greater than or equal to 1 half the sum, and it goes from n to infinity of negative 1 over 2 to the n. Does that sum converge or diverge to minus infinity? So I've got geometric series ratio a half. Converges. So this over here is going to be greater than negative infinity. You can calculate exactly what the geometric series is. I'm starting at big N. So it should be, I think, negative 1 over 2 to the n over 1 minus a half. But then I multiply by the half here, which cancels. So I think this whole thing, I think the actual answer, I believe, is negative 1 over 2 to the n. It doesn't matter what it is. All that matters is it's finite. So we've shown that, Craig's candidate, okay, it's identically 0 inside. It blows up outside. But at least at the point 1, it makes sense and returns a non-zero value. Alright? Where else should we look? Negative 1, I, minus I. We should try a few other points like that and just see, are there any other places where Craig's function works? Could this function be holomorphic? What do you think? You got a police lineup of functions, and they're asking you to pick out the holomorphic function. And you see this. Could this be a holomorphic function?
On an entire holomorphic function?
Good. So the question is, what's my domain? Let's say the domain is a circle of radius 1/2 about the origin. Yes, it's a holomorphic function. What if it's a circle of radius 2 about the origin? No. Okay. So the question of whether or not a function is holomorphic can depend on the domain. So what we've seen here is we've seen a very valuable lesson. If I want to build a function, I can't just form a product like this. So my challenge to you is, can you find a sequence of ANs, infinitely many that are distinct, such that this will converge and not be 0 except at the points AN in your sequence? I don't want to introduce any new zeros. I only want to keep the zeros that I already have. So the problem here is that my function just has too much decay. When I have this infinite product, it's crunched down to 0 if the absolute value of z is less than 1. If, instead, the absolute value of z is greater than 1, what's the problem? Diverges to infinity. So one way around this is you might want to put some constraints on the a's. Is maybe we assume the a's go off to infinity. So I want to argue, and I'm happy that you have enough so that you don't mind me doing this to you, this was a really good example you gave me. Is there any chance in hell that your example could have worked? What goes wrong with his example?
Things go to 0.
I'm sorry? Yeah, I have a what? I have an accumulation point. So because I have an accumulation point, I know that there is no way I'm not going to introduce more zeros. I'm going to introduce many more zeros. So the only chance you have to win the challenge is you have to find a function that has no accumulation points. You need a sequence of numbers going off to infinity. So unfortunately, Friday is going to be mountain day, so we won't be able to do class, but maybe something will go wrong. So think about an example of a sequence of points that goes off to infinity. And think about how we can try to fix this issue. So the most natural thing to try fails. We have to modify our method to take into account that this is being crunched down to 0 going off to infinity. What can we do? And so try to play, what's the most natural sequence to choose for the ANs? N. So try looking at that and see what happens with the product of z minus n. Okay. And the charge